Welcome to my lecture on the Poisson distribution. Okay, so the Poisson distribution is unlike any of the other discrete distributions in that we're not going to derive it from first principles. Okay, let's first talk about one of the most important things to recognize the Poisson distribution, which is its random variable, x. X is the number of occurrences per unit. And the unit can vary, but the most common one talked about, and the one that's in your book, is time, per unit time. Okay. X is often referred to, so the values that X can take is it can take on the value 0, there can be one occurrence, there could be two occurrences, and it just keeps going all the way to infinity. So X takes on all non-negative numbers. Okay. In order to recognize X, one critical thing that you're going to need to be given is what's called the parameter lambda. Lambda, this is the average value. But you can also think of it as a rate of occurrence, because after all, is going to be the average value per unit time, so it's a rate of occurrence. Okay. Another fact about the Poisson distribution is that it has density function p of x is e to the minus lambda times lambda to the x divided by x factorial. Okay. And I'm just going to rewrite part of this because I want it to be very clear what the density function is. So that's lambda to the power of x. Okay. And this is how we calculate probabilities. Calculate p of x. Okay. Okay. One thing that I have not proven yet, but that you can prove, is that this is e of x. I'm going to do that later. Okay. But in order to prove that, you'll need to know the density function. And the density function is this right here. Okay. Okay, let's do a quick example. Okay, and my example is that in a certain geographic location, tornadoes occur twice every 9 months. I'm going to ask us to calculate this first probability. So here's going to be the first one, there's going to be a second one later on. Calculate the probability there are 3 tornadoes in a 9-month period. And in case you're curious, I'll put the word exactly. 3 tornadoes in a 9-month period. Okay. And in order to answer this, I'm just going to write down my random variable x. This is going to be the number of tornadoes in a 9-month period. And I'm going to write down the value of lambda. Lambda is going to be 2 tornadoes per 9 months. Now, one thing that I really want to emphasize here is that the unit here is 9 months. And what we have here is 9 months. So we're okay to use for the value of our lambda to be just that 2. It needs to match the value of our random variable. Okay, so now we're good to calculate the probability. And let's do that. Okay, so if I want to calculate probability x equals 2, all I'm going to do is do e to the minus lambda times lambda to the x over x factorial. Okay, and now I just plug in, well, e to the minus lambda, that's a negative 2 times lambda is 2 to the x, which is 2. X factorial is 2 factorial. Then we just need to quickly calculate this on our calculator. Okay, so I believe you're going to get 0.271 or 27% chance. Okay, now let me change this question and give you a slightly different question. So part B, I'm going to ask you to calculate the probability there are 2 tornadoes in a 6-month period. Okay, so now something interesting occurred. Its unit of time is 6 months. That has to match the random variable x. X is the number of tornadoes per 6 months. Now we said lambda had the value of 2 tornadoes, I'll abbreviate that with a T, per 9 months. Okay, now I have a problem here. My problem is that this unit is 9 months and I need that to be a 6. So I'm going to do something very curious, and I'm going to multiply this by 6 over 6. And I think I'm going to get this. So notice that is unitless, but it allows me to convert it to a unit of 6 months. So this is going to be 2 times 6 tornadoes divided by 9 times 6 months. Okay, and so when I do that, I think 2 times 6 is 12 ninths tornadoes per 6 months. And of course I can simplify that a little bit, and I'll get 4 thirds of a tornado per 6 months. And I don't know about you, but this is our unit of lambda. because it matches that 6 months. But I'm yet to see 4/3 of a tornado. And fortunately, I haven't seen one tornado yet. So I'm very grateful. Okay. Now, when we calculate this probability, we're going to do probability x is equal to 2 tornadoes in 6 months. Now, you can just write probability x equals 2, but I just want to draw that out. And this is going to be e to the minus lambda times lambda to the x over x factorial. And we know what lambda is. Lambda is minus 4/3 times 4/3 to the x, which is 2, divided by 2 factorial. And then we just need to quickly type this in our calculator. And I believe we should get 0.234. So about a 23% chance that we'll see 2 tornadoes in 6 months. And it's a good thing that it went down because that intuitively makes sense. Okay, you have a smaller time frame to observe 2 tornadoes, so of course the probability should go down. Okay. One thing that I'd like to point out is that if you were to write out the probabilities, because of this form of the density function right here, you would generally see a histogram or a plot like this where the probabilities went down as x increases. Okay, and I think it's highly likely that we have very few tornadoes, 0 or 1. Then the probability that you have lots of tornadoes is very, very small. Okay, so that's the Poisson distribution. Before I end, I want to go over one last thing, which is calculating the mean in the moment generating function. So let me just do this. So here's a fact, and this is from calculus, and that's e to the z is nothing more than 1 plus z squared over 2 factorial plus z cubed over 3 factorial, and so on. That's its Taylor series. We can write that as the summation from k equals 0 to infinity of this z to the k over k factorial. Okay. Okay. And I'm going to use that fact. So I want to calculate the moment generating function. Of a Poisson. Okay. So to do that, I write down mx of t, and this is by definition the expected value of e to the t times x. Now to calculate that expected value, I write down the sum. I put e to the t times x. Then I multiply it by the probability density function. The probability density function is e to the lambda times lambda to the x over x factorial. Remember, the sum depends on the values of x. They range from 0, and they could go all the way to infinity. Now, because this e to the lambda, that doesn't involve x, I can take it out. So e to the lambda times the summation from x equals 0 to infinity. Okay. Well, I can now write down lambda to the x times e to the t times x over x factorial. And I'm going to try and fit this in on one screen. Just this next thing I'd like to write, since it's right here, we should notice that we have that x and that x. By rules of exponents, I can write lambda times e to the t, all raised to the x power, divided by x factorial. So now let me just rewrite that on the next page, and we'll take it from there. So what I have is the moment generating function is going to be e to the lambda times the summation from x equals 0 to infinity of this e to the lambda, just writing down what was on the last page, e times lambda to the t, all raised to the x power, divided by x factorial. Let's just double check. Yeah, lambda to the x. So times e to the t. And let me just double check one more time. Lambda e to the t, all raised to the x. Great. Okay. Then we also know this fact, which is that e to the z is going to be the summation from k equals 0 to infinity of z to the k divided by k factorial. Now I have an x here instead of a k, and instead of having an x there, I have a k there. But that doesn't matter. I'm going to call this little piece right here, I'm going to call this piece z. Okay. And when I do that, that tells me that my moment generating function is this e to the lambda times e to the z. And I'll write out what z is. That's lambda times e to the t. So this is e to the lambda times e to the lambda times e to the t. That's by the Taylor series for e to the z. And I can write this one more time and combine exponents, lambda times e to the t plus lambda. Okay, and that is my moment generating function right here. But I should write a better t. Okay, now if I want to calculate the mean value, I'm just going to take the derivative and evaluate at 0. Okay, so mu is going to be mx prime evaluated at 0. Let's just calculate a mx prime of t. So I need to differentiate that thing. That means using the chain rule. So this will be the derivative of the inside. Let's go back and look at that. The derivative of the inside will be the derivative of this thing right here. The derivative of lambda is a constant, is 0, but the derivative of lambda e to the t is just lambda e to the t. Now, using the chain rule, we're going to get this. Lambda, so take the derivative of the inside first. Lambda times e to the t times e to the lambda e to the t plus lambda. Now, that's our derivative. When I evaluate this at 0, I'm going to get lambda times e to the 0 times e to the lambda times e to the 0 plus lambda. Okay. So I think we're going to get just this lambda times e to the, it should be 0, but it's 2 lambda.